Let's finish up lesson 3.3 with some additional practice of our polynomial identities. Example 1, you're asked to simply multiply 2x squared plus y cubed, quantity squared. Now remember, when you see something being squared, what you're supposed to do is write it out 2 times. It's really a product of the parenthesis times itself. That would give us 2x squared plus y cubed, and then we repeat that side by side. 2x squared plus y cubed. We're going to FOIL to combine our terms. If we start with 2x squared times 2x squared, 2 times 2 is 4, x squared times x squared, when you multiply the variables, you add their exponents together. You would get x to the 4th. If we then take 2x squared times y cubed, would stay 2, and then x squared times y cubed really doesn't change, so we're going to leave that. If we do I for the inside terms, y cubed times 2x squared is a like term, 2x squared y cubed. It's the exact same term. And then if we take y cubed times y cubed, check this out. That's going to be y to the 6th. Y cubed times y cubed, you add the exponents together to get that 6. Now to combine like terms, nothing matches with the 4, x to the 4th, so we'll start with that. And then we have like terms in the middle. That means when we're adding, we combine their coefficients out in front. 2 plus 2 is 4. We have 4x squared y cubed. And then there's that y6th at the end that doesn't have a like term. Our final answer, 4x to the 4th plus 4x squared y cubed plus y to the 6th. When asked to factor, make sure you decide, are you working with perfect squares or perfect cubes? And recognizing that if something isn't factorable, it would be considered prime. Let's try that first one. 9m to the 4th minus 25n to the 6th. Well, kind of right out of the gate, I recognize that 9 and 25 are perfect squares. So is there a way to write m to the 4th and n to the 6th as perfect squares? M to the 4th could be rewritten as m squared squared. I know, kind of weird. And n to the 6th, if we think about something being squared, we could do n to the 3rd power being squared. And that would give us n to the 6th. So this would technically mean that 9 would be 3 squared. So 9m to the 4th is the same as 3m squared squared. Ooh, wrap your head around that for a second. If we took 3m squared times 3m squared, 3 times 3 would be 9. M squared times m squared, you'd add those exponents and you'd get m to the 4th. And then we have minus in between. And then if we have 25, n to the 6th, 25 would break down to 5 squared. And then if we take n cubed and square it, that would be a perfect square. Since this is subtraction, this is a difference of perfect squares. And this breaks down into the sum and the difference of those parentheses. That means we would have 3m squared plus 5n cubed times 3m squared minus 5n cubed. Believe it or not, that is the factored form of 9m to the 4th minus 25n to the 6th. Let's try the next one. Again, the same idea. We have m to the 8th minus 9n to the 10th. Well, m to the 8th is an even number, so it might be easy to make it a perfect square. And we know 9 is a perfect square. So let's try to see if this is a difference of perfect squares. If we have m to the 8th, that would be the same as m to the 4th squared. And then if you took m to the 4th times m to the 4th, you'd add the exponents together and it would get you right back at 8. 9, n to the 10th, I guess I can put the 9 with it. On the last example, we just did the number, or the variables. But 9 would break down into 3. And now we have n to the 10th. Again, that's another even number. If we separate that as n to the 5th, but then we square it, that would give us n to the 10th. We now have m to the 4th squared minus 3n to the 5th squared. Bet you never thought you'd hear that. If it's a difference of two squares again, this is going to break apart into the sum and the product of the sum and the difference of those parentheses. That would give us m to the 4th plus 3n to the 5th times m to the 4th minus 3n to the 5th. That is the factored product of m to the 8th minus 9n to the 10th. Okay, we have just a couple more. Example C, x cubed minus 216. Since we see x cubed, we may have to think, okay, this is likely a perfect cube, not a perfect square. So 216, if you think about that list on the front of our notes from part 1, 216 is the same as 6 to the 3rd power. So this is x cubed minus 6 cubed. And the template for this is a small parenthesis and a big parenthesis. In the small parenthesis, we just do their difference. We just subtract them, x minus 6. In the big parenthesis, we take the first term, which is x, and we square it. And then remember the rule for subtraction. It goes minus in that first parenthesis, and then plus and plus in the second parenthesis. We take x times 6, and then we do plus. We take 6 and we square it. Let's clean that up just a little bit. And we get x minus 6 times x squared plus 6x plus 36. And remember our rule for this second part? Even though it looks like it might factor, it will never factor further than that trinomial part. Oh boy, one more. Let's take a look at example D. I need to slide the screen over to give me a little bit more room on this one. All right, thinking about perfect cubes on the front, I see 27 and 343. Right away, those definitely do not look like perfect squares. And then we have x to the 9th, which we couldn't make a perfect square. Y to the 6th we could, but the rest of them aren't perfect squares, so they're likely going to be perfect cubes. So let's see what we can do with this. 27, x to the 9th. Well, I remember from the other side, 27 is the same as 3 cubed, but x to the 9th, how can we make that a perfect cube? Well, if we take x cubed and then cube the entire parenthesis, that means we'd have to write 3 parentheses out. And x cubed times x cubed times x cubed would in fact give us x to the 9th. What about 343 y to the 6th? Well, if you remember on the other side, 343, that was the same as 7 cubed. And then y to the 6th, what number could we multiply by itself 3 times to get 6? That would be y squared. This is going to get messy. If we have 27 x to the 9th plus 343 y to the 6th, as perfect squares, they would be 3x cubed, as perfect cubes, 3x cubed cubed plus 7y squared cubed. Yikes. We'll have a little parenthesis and a big parenthesis, but we're writing a lot of content in there. Make sure your parentheses are big enough to fit everything we're going to write. The first parenthesis, when it's addition, is addition. So we're going to start off with 3x cubed plus 7y squared. Luckily, they're not like terms. It's that next parenthesis that we have to be super careful how we write it out. The first term is supposed to be squared. What that means is we need to take 3x cubed and square it. We'll have to figure out what that's going to look like. And then for this template, if it's addition in that first parenthesis, we put a minus in the second parenthesis. And then we have to take the terms and multiply them with each other. I may not have enough space. Oh boy. We're going to have to multiply those together. So I'm going to move that parenthesis over just a smidge to make sure I have enough room. Oh, okay, we'll see. The second one is plus now. But now we take that 7y squared, and we have to square that. We need to simplify that big parenthesis. We can do this. Our first parenthesis, 3x cubed plus 7y squared. Luckily, nothing to do there. In that second parenthesis, if we take 3 and square it, 3 times 3 is 9. X cubed squared, we'd have 2 of them, and 3 plus 3 would be 6. So that's 9x to the 6th. Minus 3 times 7 is 21. X cubed times y squared is x cubed y squared. Plus 7y squared squared, well, 7 squared is 49. And y squared would be y squared times y squared. That would be y to the 4th. Wow, that's a pretty extensive example of how to factor the sum of two perfect cubes. And this finishes our lesson, one more smiley face, for 3.3.